Differential equations, we are in the 4.7 e-learning assignment again, which is really like a review for our last assessment. And we are looking at not a Cauchy-Euler differential equation, but really the homogeneous, well, in this case, it's a non-homogeneous second order differential equation. We're going to use methods that we learned in 4.3. What that involves, of course, pardon me, gotta get this pen going, is, we look just for a moment at a homogeneous second order differential equation, and we'd work with the assumption that e to the mx, e to some power, would in fact yield a solution. Again, you don't have to take successive derivatives and plug it in and simplify. We're going to really get to what we call a characteristic equation. And as we solve, the square root of -1 is an I. And, you can see that there's no real component to that. That's just going to be m is equal to 0 plus or minus an I. And what we saw in the past is when we had, these complex solutions like alpha plus beta I, we assumed that our answer, this is some nice review, our characteristic solution here would look something like this. And e to the 0x, alpha is 0, that's just going to wipe out to a 1. And then we'll be left just with a cosine of beta is 1 also, that's a 1x. And then we'd have a sine of 1x also. So this is what we call our complementary solution to this non-homogeneous differential equation. That's going to be part of our solution. But then, of course, our focus is going to come to this right-hand side. And we're going to say, now, wait a minute. We no longer have 0 there. We have x squared plus 1. And that is, in fact, a quadratic. So for a particular solution, we're going to, just as we could see in a chart here, say that we believe that there'd be some general quadratic that would be a solution. And taking this derivative, oh my goodness, it's going to be so much faster than the previous situation. Sometimes things just work out that way. We're going to solve by the method of undetermined coefficients. The second derivative is a 2a. The original equation would be an ax squared plus bx plus c. And on the right side, please pay attention to how I'm also putting in a 0x. We're going to real quickly just clean this up a little. We'll have an ax squared. Here we have a bx. For our constant, we have a c plus 2a. And then, thankfully, we just pretty much mix and match here. We can say, pay attention to, the lead coefficient. What's in front of x squared? Well, 1. Well, that means that a will have to equal a 1. Next, you could come over here and say, well, what's in front of the x? Well, we have b on the left side, but on the right side we have a 0. And then finally, right here, we have a c plus 2a. It's not going to take us too long to finish that up. We'll go c plus 2a is equal to a 1. But again, now we know what a is. It's 2 times a 1, which is just a 2. And when we subtract a 2 from both sides, we'll get c is equal to -1. So our particular solution which we really have here, and can even bring it down. Once we know that a is 1, we'll have an x squared. Our b is 0, so that's not even going to factor in. 0x completely goes away. And our c is a -1, so we could just write it that way. So our general solution is the complementary solution for the homogeneous differential equation, setting it equal to 0. And then we add to our particular. So right now things are looking, just fine, I hope. But there is an additional step we're going to have to take. There's a reason why they gave us y of 0 equals 5 and y of 1 equals 0. So y of 0 equals 5 and y of 1 equals 0 is what we had. The reason why they've given that to us is so that we could find what C1 and C2 really are equal to. Now, pay attention here. Sometimes kids will really wonder if this is a typo because both of your initial conditions are actually for y and not for the derivative. Sometimes you'll be given that, and this is not a typo. So let's just start by working with the point 0, 5, letting x equal 0 and letting y equal 5. When we get that, our left side is a 5, and we'll have the cosine of 0. Well, the sine of 0, that's going to be nice, isn't it? The sine of 0 is 0. Cosine of 0 is just a 1. And my goodness, you are going to be able to solve for C1 so amazingly quick. You're done right now. You know that C1 is actually a 6. But we're also going to work with this y1 of 0. That means that we've got the point 1, 0, that x is equal to 1 when y is equal to 0. Well, again, what we're really getting at, guys, is working right here and plugging in x equals 1 and letting y equal 0. So I'm even going to recopy this really to make this pop out. Sometimes the fact that you're plugging in a 1 right here is exactly what will trouble kids quite a bit. Look, you know your y is 0. By the way, you now know that C1 is a 6. That's lovely. That's great. But I think it's right here where kids are saying, well, what about this 1? What's happening here? What's the cosine of 1? It's 1 radian, guys. We don't know what the cosine of 1 radian is without a calculator. 1 radian is kind of close to 60 degrees. It's not exact, of course, but, it's just some angle measurement. By the way, here, the 1 squared is 1, 1 minus 1. That's just a 0, isn't it? So, what do? Well, subtract that cosine of 1, 6 cosine of 1 from both sides. And now divide by the sine of 1. And cosine over sine can be written more simply as cotangent. So right here, guys, we've got our C2. So we can come back to our general equation here and say, now I know that C1 is the number 6. C2, gosh, this looks funny, but don't worry about that. And put some parentheses around the cotangent of 1. The cotangent of 1 is just some decimal, some coefficient, some fixed real number. And guys, that's what your final answer is going to be.